finish autoencoder today, and then we will move forward to discussing the model for segmentation. Okay. But before that, you have done with your assignment number 4, but I still want you to take a look. The slide here is downloaded from Stanford University, okay, led by Fei Li, okay, it's a very famous. She's the one proposed the ImageNet, okay, data set in the early days. But anyway, I still want you to give you a lot of detail, but the one I want you to take a look, although you have done it in your assignment number 4, okay, you talk about the history about CN model, but the one I still would like to talk about is, let's go for, because whenever you are using a convolutional based CN model, the natural choice or the baseline model usually you will just select VGG, okay, or residual net, okay. And now you got a third choice, convolutional next, okay, which also including your assignment number 4. But the one I would like to mention is the VGG. Let me say that one more time, okay? Because it's so popular. Whenever you use a CN-based model or you want to develop your own model, you can always refer to this model as a baseline, okay? Okay, here's how, this is the input, okay? Then you go for convolution, max pooling. Convolution, max pooling. If you want your model to be simple, then you can just stop here. And then it goes for, okay, make a note here, something wrong. This should be convolution. Then you will connect to 3 convolution layer, not 2. Otherwise, you won't get 16. Come 1, 2, 3, 4. Should be 5, 6, 7, 8, 9, 10, 11, 12, 13, and 3 fully connected layers. It adds up to 16. So this model, it missed something. So anyway, convolution, max pooling, convolution, max pooling, then we'll have 3 consecutive convolution, then max pooling, 3 convolution layer. Okay, or you can go for the VGG19 again. Convolution, max pooling, convolution, max pooling. This is also wrong. Okay, you need 3 convolution layer. Otherwise, you cannot get 19 layers. Okay, and you for each layer you use only a 3 by 3. Okay, the kernel size. So it is very compact. Okay, that's the one you want to develop your own. Is highly recommended, but it does not have to be 16, as I just mentioned. It may be just 6 convolution, max pooling, convolution, max pooling, or 2 more convolution. Okay, you take each one as a block. Okay, that'll be good enough. Okay, and you may or you may not have to use max pooling, especially you go the strike by 2 for the convolution, then you will reduce the size, okay, by a factor of 2 after every convolution. So it's still up to you, okay? But the standard one is we use a 3x3, okay, convolution. The standard 2x2 max pooling with a stride of 2. That's it. Okay, that's the only thing you need to keep in mind for the VGG. Don't just use it, but you need to know the architecture. Okay. Okay, and it talk about what are the total number of the parameter. And the architecture here is correct. Convolution, convolution pooling, convolution, convolution pooling, and then 3 convolution pooling. This architecture is correct. Okay, but the figure here, something wrong. Okay. Okay, that's the only thing I would like to take a look. And also the inception layer, here's architecture. Okay, you can take a look at inception layer. And then the okay, give you a lot of details information, and then the residual net is up to 152. Okay. Most of the case, I don't think you need 152. Okay, unless you are very large data set and you have thousands classes. Okay, and here's the basic architecture. Okay, just keep repeating. Okay, you can take up this as a block. Okay, as a block. Input, no matter it's from original imagery or from the previous feature map. Convolution, then and also you bypass these two. Okay, so that's why you call it procedure. Okay, then just keep repeating all the procedures here. Okay, that's because the bypass operation so that it can go very, very deep. Okay, without gradient vanish. Okay, that's all I want to say about it. Okay, and now we can go back to our autoencoder. I already introduced CAE, okay, and VAE, variational autoencoder. Especially variational autoencoder is very popular, okay, for visual extraction, for image reconstruction or image generation. A lot of more advanced models are based on the VAE. Okay. Okay, we already talked about this, but I still recommend to go through the detail for VAE. Okay. Okay, let me summarize one more time. Autoencoder is because the input is exactly the same as the output. So in this case, you don't need any human intervention. You don't need manual annotation or manual labeling. Okay. But the process basically is based on variational inference. Okay, but trained with the encoder neural network model, and also generate or reconstruct the image also by a neural network model. For VAE, basically in the original paper, both are based on CNN. Okay, they are both based on CNN. Okay. And for the user, you need to specify the dimension of the latent variable. Okay, that's something you need to. I just keep saying if the dimension of Z, the latent variable, is quite large, then you might need a lot of time to train the model. But if the dimension is very slow, then it cannot reconstruct the details of the original image. So that's the choice. Okay, depends on your application. For anomaly detection, you have two choices. Okay, you have two choices to measure the difference. One is based on the mean square error, the reconstruction error. You can base on the reconstruction error. Okay, based on the reconstruction error. Okay, this is the input. And this is the reconstruction. Okay? Especially for unsupervised learning, usually we train only one class sample. In manufacturing application, especially for the defect detection, if you only have a very few sample of defect product, then we just train with normal sample. And then, because this model is trained with only a normal sample, when you have an outlier or defect, then it cannot reconstruct well about the input because the Z it learned will be quite different, okay, from the outlier. So anyway, you can simply base on this to set up the threshold. Okay, if I call it delta X. So if the reconstruction error is quite large, that again, you need to set up the threshold. Okay. Most of the case, we can simply given by, okay, this is the reconstruction error, the mean reconstruction error from all your training sample. This is the standard deviation, okay, from the reconstruction error of all training sample. K will be the control. This is exactly just like the SPC, okay, process control. You can set up, okay, you can always start it from three sigma. 三倍标准差 but depending on your sample, okay, you need to try out K equal to 1 or 2 or 3 or 1.5 and pick out the one, no, but that's fit. Okay, so if the test image has reconstruction error, okay, larger than some threshold, then you will say this is an outlier. Okay, this could be the first. The second way to do it is based on what? The latent variable. or we can call it latent vector, okay? Z, which is the representative, okay, features learned from your VAE, or actually you can apply also CAE, that'll be fine, okay? So in this case, you can calculate the test image with the mean, for example, okay? You can compare it with the mean from all the training, okay? The training sample. Or the better way, if you can measure the probability for the test image, okay? Again, because your model is trained with a normal sample, right? So whenever here comes an outlier or defect, then the representative variable will be quite different from the normal one or the training sample. That's the idea. So either you can base on the difference of these two vectors, or you can simply calculate the probability, okay? And how can you derive the probability? Again, based on your training sample. Or you can use Z, then we can input Z to a machine learning algorithm, okay? Such as SVM, Bayesian probability, or random forest. That would be the top for the DP course. Okay, that would be. What I'm trying to say, you can go back to the traditional machine learning. It does not have to be. So in some case, it could be better just purely use neural network. So in this case, the autoencoder plays the role for feature extraction. That's it. Okay, just extract feature. But for classification, maybe then we can go for any machine learning algorithm. Okay, and how to calculate the probability or use any, that would be the topic. Okay, for data pattern class next semester. Okay. Okay, so let's talk about the one last thing I just want to mention is again for VAE, the good thing must keep in mind the latent variable is learned not just like the CAE, because the latent variable given by CAE is fixed. Okay, it's fixed. But for VAE, for each feature, then you will follow some distribution, okay, given by the mean and standard deviation from the output of your encoder. Okay, that's the difference. So you must be very careful when you apply VAE. Even with exactly the same input, every time you will get exactly the same output. It will be the same for CAE. If the input is fixed, then the output will be also fit for a trend CAE. But for VAE, it won't be the same. But that could be the idea. So it depends on what is your application. If you want to use the VAE to generate a variety of images, then you have to better go for VAE. Then by changing the representative, okay, features. But for CAE, you cannot do it. There's no way you can do it. Okay. Okay, so that's it. And one more thing here, the loss function for VAE, it contains two terms. The very first term is based on reconstruction error. Okay. In the original model, the reconstruction error is given by the maximum likelihood, but it's too difficult to solve or implement. So usually, most of the case, the reconstruction error for programming implementation is given by mean square error or given by the cross entropy. And the K term, because we both assume P will follow follow the standard normal distribution, and also Q will be also follow Gaussian distribution. Okay, with some you estimate the mean and standard deviation. Here it says without this term, okay, for CAE, it basically is only relied on the reconstruction error, right? But for VAE, it further limit or set up the constraint for the possible latent distribution of the latent variable with this regularization. And I put a note here somewhere before I said it, because here just go through that. Okay, I don't have a time. Here is ELBD where I put it. It's called evidence roller bound decomposition. It says our objective function is only the roller bound. It's only a roller bound, which means what? The solution you get is not the truly optimal solution. And the truly objective function is not possible to derive. So it simply just set up, it just find the evidence roller bound decomposition. So always keep in mind, okay, the image you got, it may not be the optimal solution, or it may not fully reconstruct the original image, but it's very close, okay? That it needs something that's the limitation about the VAE, because the objective, okay? This is the truly objective, but to solve the problem too difficult, so it just draw up some of the term, okay? Then come up this is only the roller bound of the loss function, okay? So that's one thing you need to remember. And finally, I mentioned here what would happen if we don't have the regularization term, which is the Carroll divergence, which means if you don't set up the restriction on the latent variable z, when you try to recognize or represent, I put an example here, a printed A, okay, or a letter A, okay, A, B, C, A. They have different fonts, okay, like printed A and handwritten A, okay. Then they will have different representative features. In some cases, this is what we expect. But in a lot of cases, A is A, no matter what the font size is. You know what I'm saying? 也就是说，假如你是关心它是不是 A， 它这个 A 呢，它是用手写的还是印刷？印刷字体你也知道可以有几十种 ，right? You have a lot of printed pattern for A. But if you don't set up the regularization, they will have different Latin representations. So you must determine if this is good for your application or not. So for some application, you might distinguish the difference between the print A and handwritten A. Then in this case, you must be very careful, okay, to select the model, okay? So after you finish the class, and no matter for your work or for your job later on, you could have 100, if not thousands, different models that can be applied, okay, for the task. But you need to select which one will be the best for your application, okay? So that's about CAE, VAE, okay? We are done, and I provide the programming code, okay? Downloaded from the website, and some is provided by the graduate students from the lab, okay, for our machine vision lab. Okay, they give you all the details, so you can simply just follow, okay? You have, you want to know the more details, okay, how it works, okay? So you can just follow. For CAE and for VAE, okay? Okay, and I mentioned before, if you change the Z value, okay, a little bit, then we'll change the reconstruct the image a little bit. That could be good for, especially for image augmentation. Okay? 好，你要影像扩增。Especially in manufacturing, you may not have too many defects. Okay, sample. Then you can use this based on a few defect sample that you collected on hand, and then you can apply the model to generate or synthesize more defect, so that you can train a better, robust and reliable, classification model, okay, and for your own application. That's the idea. Okay, after pages 32, all this information here is provided by the machine vision lab. Okay, for the graduate student, they not from Carl's, okay, but for some student graduate many a few years ago. Okay, so it gives you all the details how you set up the. Here's take a look at the convolution. Okay, this got to be it go all the way for convolution. Okay, convolution. Okay, and then upsample, and this must be for decoder. Okay, this is for decoder. So it could. And how it set up the activation function and all the parameters. Okay, so it give you some good reference for that. Okay, and then you talk about the VAE for defect detection. The training is only for with normal sample. Okay, and it give you a lot of the detailed architecture. Okay, for this one, see that the encoder. Okay, I'm not quite sure do we really need this many convolution layers. Okay, but it's up to you. Okay, and here for this case here, it uses up to 100. Okay. Latent variable. 就是那个变数它用100个. It can change it. It does not have to be fixed to be 100. Okay, you use 100. Okay, and then based on the output mean and standard deviation, you calculate the z value, and that's it. Okay, and then this for decoder. And for decoder, you use transpose. Okay, and remember. Talk about the transpose. Okay, we can upsample it. Okay, without using upsample, you simply go for the transpose convolution. Okay, transpose convolution. Okay, so okay, you can take a look at the scale, and finally, it also show you the Carroll divergence, okay, parameter in a set. Okay, so that's all about autoencoder. Okay, for unsupervised learning. Okay. Okay, and I mentioned this, right? You can go for the nearest neighbor for upsampling, or use interpolation. Okay, by the simple linear or cubic, it is non-linear. It's a by, that's because we're talking about image. It's two-dimensional. We have x and y. 好，会叫 by 是因为我们谈的是二维内差，因为我们的影像有 x 跟 y. Okay, but the idea just like any interpolation in one dimension. And here's more, okay, provided by Carroll. You can select the best one that will generate more accurate or more details about the reconstruction image. Okay. Okay, so that's it. Okay, and I also finally I give you this example, right? Original image, okay, and always we just insert 0, okay, row by row, okay, row by row and column by column. So we can upscale the original image from 3 by 3 to 6 by 6. But the kernel size is still the same, 3 by 3. Okay, that's 3 by 3. We use 3 by 3. Well, actually, there's another convolution called dilate. If I have time, I will talk about it, called dilate. For the dilate convolution, it inserts 0 here. So your dilate filter will become, if you insert 0, it can be either 5 by 5 or 6 by 6. But the number of parameters is still only 9. That's the idea. You know what I'm saying? But it can look a wider field, because the field it just look for the 3 by 3 neighborhood, right? But if we insert 0, just something like this, then you can look for a wider field for 6 by 6. You can look for more neighboring hood. That's so-called dilate. Just exactly that what you have learned about dilation in morphology. Okay. But anyway, for decompose, it just show you how we do the convolution. Okay. Then the result will be 6 by 6. Okay. So that's it. And this just show you how we do the one-dimensional interpolation, two-dimensional interpolation. Okay, and it also show you this one you may not be familiar with. Okay, called length zones. Okay, it's a kind of sine function. Okay. We have a parameter here called A. Here's the idea. If okay, take one-dimensional example. If this is our profile or signal, then you use a lot of different sine function to fit. Everyone follow me? You use a different sine function, the combinational sine function. If you have this point and this point, you want to interpolate, okay, then maybe there's something for example, if you have something like this, okay, maybe for cubic, then maybe you will interpolate by this. But for this case here, for different point, you will use different sine function, okay, locally to fit. So it theoretically, you can have a better fit, okay, for the value, okay, for the value. That's the only idea. When you apply, let me go back to, as I mentioned, for linear interpolation, oops, it's not here. It shows you a lot. Here you can see 3 and 5, right? That's the parameter of A. Okay, A. Okay, that's the parameter of A. And you can try out which one will give you the better result. But anyway, you need to. At the cost of computation time might increase. Okay, here's the parameter here. Okay, A here. It could be 3 or 5 or any value, you can change it. Oh, I put it here, okay. Okay, it could be 3 and A could be 5. Okay, it provides these two choices. Okay, so I mentioned something about diffusion encoder and mass autoencoder. They are two most up-to-date model for autoencoder. Okay, so let me just say something about what. Why is not? Did I provide anything? I thought you have. So this is all you have?
No, we have different. It have the content. It contain the content.
No, this is my last page. You give me the old version of 有新的嘛哈，对吧？ So the TADM to provide the up-to-date version. Okay. This is the old version. Okay. Anyway, let me see if I can show you. It's okay. I have something. Not. No, that's okay. It's okay. Okay. Just give the idea. We don't have too much time on it. Let me see if this is good enough for. This is no. This is okay. Let me show you the other one. Okay, again, it's in the supplementary material. Okay, it could be different from the version I provide you. This gives you some more detail, but that's good. I'll just show you the idea. Okay, here's the idea. Okay. Again, autoencoder is still autoencoder. Of course, diffusion can be expanded for any different kinds of application. Does not have to be. But the idea is like this. Okay, take a look here. This is the input data. Okay, this is the input data. It called diffusion. That's because we diffuse the noise gradually, okay, into the image. So like this the forward diffusion process. This is the input. Then we add the noise gradually, okay. So this code for this case here, you may code it 1, 2, 3, 4, 5, 6, 7. We have 7 time steps for diffusion. So we add the noise gradually until you cannot see anything here. Okay, or you can see it just the rate noise. Now here, and we go for reverse the noise process. We're starting from here, then this, or you can call this backward diffusion process. We're starting from XT, the quiet noise, then we estimate or try to do the noise from the image, okay? And from here, you can see something better. And then we do further, okay, to remove more noise, and eventually, and hopefully, we can convert the noise image into the original data. That's the idea about diffusion. So basically, the training will take longer compared with CAE or VAE. Well, actually, you can also think of this, the diffusion process, as a VAE. You can think of VAE just a one step, okay, just a one step input image encoding to get the latent variable and use the latent variable to reconstruct the image. But for diffusion, you will add the noise, okay, gradually. And then it will try to recover, okay, the image from the previous step. With this approach, generally the image has a higher quality compared to VAE. 跟 VAE 它的影像的品质会非常好。Okay, as I mentioned, the stable diffusion or most very popular image generator software is based on diffusion model. It does not based on VAE. It does not based on GAN. Okay, which GAN will be another topic later on. Okay, but anyway, that's the idea. So if you go back, take a look. It goes like this. Okay, for X0 is the original image, and we do it forward. Okay, we do it forward. We to add, okay, the noise. Okay, and then from XT, okay, T will be the final step. Then we goes back, okay, then we goes back. Okay, given XT, we estimate what should be the probability, okay, or what should be the best estimate image at T minus 1. This is something you need to learn. Okay, so that's what I'm saying. It somehow look like the VAE. When you put theta here, it means what? It's going to represent or going to learn by a neural network. Okay, you will be learned by a neural network. Now, given XT, we try to estimate what should be the output. In real application, it goes like this. We have the encoder. Again, we still have the Z, okay? And then we have the decoder. Now, here's how it learns. Given X0 initially, we plus some noise. Then we try to learn to get the output X0. Okay, try to get X. That's the first step. But after that, whenever we got some X, okay, we get the reconstructed X. We plus, suppose this is T. Okay, at time step T, we plus a random noise. Okay, the random noise, it got to be, again, it assumes is standard normal distribution. And then we use it as the input. Okay, we use it as the input. Then we get the output. You know what I'm saying? And every time you add more noise. Okay? Or you can do this forward. Okay? X0, at T minus 1, we add more noise. And later on, okay, we try to, but that's the usual case. Okay, given X, we estimate that this is the reconstructed image. That's what we estimate. And then we add noise. We add noise. And then take this as the input to retrain the encoder. And hopefully we can train a very robust or very representative latent variable. That's the idea. Okay, that's the idea. Why we can obtain a good quality image after the process. Okay, just keep at the random noise. Okay, so what it say here for the decoder, for the original image, and then you process the noise with general T. That's the 4. Okay, and we simply assume it's a Gaussian function. But for the backward, and we take xi, then we plus noise, and we estimate. We try decoder. You try to eliminate the random noise. So anyway, the objective could be, or your loss function could be, simply just try to minimize the estimated noise. Okay. And the noise you generate here. Okay? You know what I'm saying? This is given, okay, after you generate reconstruction error. So this is the noise you generate, and this is the noise for the input and the reconstructed. What is left will be the noise. Right? Everyone follow me? This is the input. The input contains the noise, and we try to reconstruct it, which means we try to denoise. So you are trying to minimize. Okay, this is the estimate noise. And this is the ground truth noise, because it's added by your standard normal distribution. Right? This is the ground truth. This is the ground truth noise. Okay, and then this is the noise at time t. So we just keep repeating this. There are a lot of ways, or you can simply, based on the reconstruction error, compare with your original image. That'll be fine. There's so many different versions of the diffusion model, but this is one of the explanation, okay? Because we're talking about the noise, then we simply focus on the noise. Just the noise. We try to minimize the noise. So if you can minimize noise, and eventually, we can remove all the noises and make it back to the original image. And you can retain all the fine detail and high quality image. So if you have a chance to apply the diffusion model, basically you have 3 parameters for the user. Okay, it could be more than 3, but you will have a very. The first will be the time step for training. For this case, as I say, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and so usually you will need to use up to 100 or 200. But nowadays, some say you only equal to 4. I didn't try the big, but for my experience, you might need to go for a 1. Depends on what is the image quality you are looking for. Okay, that's the first one for training. Now, once you train the model, whenever you input a new image, then you still need to add noise. So that will be another second parameter. The time step, you will do the denoise. And usually that will be less than the training time step. It usually will just take 10 or 20. 就是一开始假如你训练可能都要100、200，那真正完了在用的时候呢，大概只要10或更少就可以完成了。The other parameter will be this dimension, the dimension. The user you need to give the dimension, especially for the autoencoders. Okay, so that's the basic idea for diffusion model. Okay. Okay, so that's the about diffusion, very very popular, okay, and use a lot. I put it here. The one you are quite familiar with, stable diffusion, dot 2, dot E, or image generation by Google. They all based on diffusion. They are not based on GN or any or flow or flow model. Or actually, another flow is also autoencoded. Okay, called flow base. Okay, autoencoded, but seems nobody talk about. Once we have the diffusion, nobody talk about it. So I decided to remove it. I don't have a time to, but that will be another one. Okay. And finally, about the autoencoder is the mask. Okay, that was it. And then we can go for the semantic segmentation. Okay. Okay, let's take a break. And also the mixture. Okay, the mixture is also based on the diffusion. Okay.